Okay, today we're going to look at the apportionment chapter. Apportionment is the problem of a fixed number of things among groups of different sizes. We have 4 apportionment rules. The things being divided up can exist only in whole numbers. Number 2, we must use all of the things being divided up and we cannot use any more. Number 3, each group must get at least one of the things being divided up. Number 4, the number of things assigned to each group should be at least approximately proportional to the population of the group. So, what are we talking about here? Well, the best example I can come up with where apportionment is when determining how many members of the House of Representatives each state receives. This is done using apportionment, and throughout history it has been done several different ways, and that's what we're going to look at. I believe a total of 5 different ways to do apportionment. Most of them have been used at some time or another. So it was Hamilton. Hamilton's method is to determine how many people each representative should represent. We do this by dividing the total population of all the states by the total number of representatives. This is called the divisor. Then we divide each state population by the divisor to determine how many representatives it should have. We record this answer to several decimal points. This is called the quota. Now we're going to cut off all the decimal parts of all the quotas, but we're not going to forget them. These are called the lower quotas. Add up the remaining whole numbers. This answer will always be less than or equal to the total number of representatives. Assuming that the total from step 3 was less than the total of representatives, assign the remaining representatives one each to the states whose decimal parts of the quota are largest until the desired total is reached. Make sure that each state ends with at least one representative. So that's where places like Alaska and Montana, even though their populations may be low, they still get one representative in the House. So, Delaware. We're going to look on the state level. Delaware has 3 counties, not Newcastle and Sussex. The Delaware State House of Representatives, 41 members. So we're talking about the state house. If Delaware wants to divide these representatives along county lines, which is not required, but suppose they do, we'll use Hamilton's method to apportion them. The population of the counties are as follows, and this is from the 2010 census. So we have our total right here. Now we're going to divide that by 41. So we're going to take 897,934 and divide it by 41. And what do we end up? 97934 divided by 41. And it gives us 21,900.82927. So our next step is find a quota. And I'm just going to continue here. Now, what we do is we divide each population by this divisor here. That's why it's called a divisor. So let's do that. And this first one is 7.411, and I'm just going to go to 4 decimals. That should be sufficient for what we need. Take the second one, divide. And I get 24.5871. And then the last one, and we get 9.0017. Okay, now the next thing we do is we simply drop the decimals. And this is our lower quota. This would be 7, this would be 24, and this would be 9. Add that up, and we get a total of 40. So this tells us we have one more representative to dole out. And according to Hamilton's method, it's the one with the highest decimal part. That just so happens to be this one here. So our final setup is 7, 25, and 9, which leaves us 41. And that is how Hamilton's method works. Okay, here's another example with Hamilton's method. At this time, I'm not going to do multiple examples of the same thing. We can do this in online office hour meetings, or I could help you individually if you need it. I want to just give you a general idea how to do it, and we'll see how it goes. These are not overly difficult. They just can be quite time consuming. So then we get to the quota rule. The quota rule says that the final number of representatives a state gets should be within one of that state's quota. Since we're dealing with whole numbers for our final answers, that means that each state should either go up to the next whole number above its quota or down to the next whole number of its quota. So our next method is Jefferson's method. In Jefferson's method, we determine how many people representatives should represent. And we do this by dividing the total population by all the states by the total number of representatives. This answer is called the standard divisor in this case, as opposed to just divisor. Divide each state's population by the divisor to determine how many representatives it should have. Record this answer to several decimal places. This is called the quota again. Cut off all the decimal parts of all the quotas, but don't forget them. These are the lower quotas. Add up the remaining whole numbers. This answer will always be less than or equal to the total number of representatives, just like in the previous one. If the total from step 3 has less than the total number of representatives, reduce the divisor and recalculate the quota and allocation. Continue doing this until the total in step 3 is equal to the total number of representatives. The divisor we end up using is called the modified divisor or adjusted divisor. So let's look at this again. Okay, so let's look at example 4 on applied Jefferson. So the first thing we need to do is figure out how many representatives we need, and that was Rhode Island has 75 seats. So the first thing we need to do is take our total population, 1,052,567, and divide it by 75. And if we do that, we get 14034.22667. And then we're going to divide each individual population by the divisor here. And we get 3.5538, 11.8395, 5.9091, 44.6528, and 9.0488. So dropping the decimals, I have for lower quotas 3, 11, 5, 44, and 9, and that gives me 72. So now what I need to do is try again. Go back up here, see what we're supposed to do. Okay, if the total in step 3 is less than the total number, reduce the divisor and recalculate. So we need to reduce our divisor. Okay, so this is the hard part about this, finding a number. I'm going to use a divisor of 13,750. And let's start at the bottom here. I get a new lower quota of 9.2348 here. And here I get 45.5758. And here I get 6.0282. And here I get 3.6273. And I don't have this one. And here I get 12.0842. So here I have 3. This goes to 12. This goes to 6. This goes to 45. And that stays at 9, which gives me 7. So this is my apportionment there, using Hamilton's. Again, these things can be time-consuming and tedious. If memory serves me correct, the only one on an exam is Hamilton's. I highly recommend setting up spreadsheets to do these. They work out a lot better. Okay, the next method is Webster's method. Determine how many people each representative should represent, and do this by dividing the total population of states by the total number. So this is the same as the others. This is the same as the other. Now it says round all quotas to the nearest whole number, but down. If the total from step 3 is less than the total, is reduced, you calculate the quota, and allocation. If the total from step 3 is larger than the total number of representatives, increase the divisor and recalculate the quota and allocations. Continue doing this until the total in step 3 is equal to the total number of representatives. So we're going to Delaware data. So what do we have? We had the counties. We had Kent, Newcastle, and Sussex. And we had the population, which was 162310. Okay, then we have our divisor there, which is the same as before. We do all our division, and we get our quotas of 7.4111, 24.5872, and 9.0017. Now it says round to the nearest whole numbers. 7.4 rounds down to 7. 24.5872 rounds up to 25. And 9.0017 rounds down, and I believe 41. So that is our breakdown. And I believe that was the same as we received before. So that one's not too difficult unless it doesn't come out right. And again, as I said, this will not be on the exam. It will be in the homework, though. You can set up a spreadsheet to do all the multiplication and division for you, and then you won't have to do it manually. Okay, number 6 is the Rhode Island data. I'm going to leave that one alone. Okay, then we have something called the Belinsky-Young impossibility theorem. The Belinsky-Young impossibility theorem shows that any apportionment method which always follows the quota rule will be subject to the possibility of paradoxes like the Alabama new states of population paradoxes. In other words, you can choose a method that avoids these paradoxes, but only if we're willing to give up the guarantee of the following quota rule. So the next method we're going to deal with is called the Huntington-Hill method. So again, the first step is the same. Second step is the same. Here's where it's different. So step 3 is cut off the decimal part of the quota to obtain the lower quota, which we'll call n, and then compute the square root of n times n plus 1, which is a geometric mean of the lower quota, and one value lower or higher. If the quota is larger than the geometric mean, round up. If the quota is smaller than the geometric mean, round down. Add up the resulting whole numbers to get the initial allocation. If the total from step 4 was less than the total number of representatives, reduce the divisor and recalculate the quota and allocation. Total from step 4 was larger than the total number of representatives, increase the divisor and recalculate the quota and allocation. Continue doing this until the total in step 4 is equal to the number of representatives. The divisor we end up using is called the modified divisor or adjusted divisor. So let's go back to our Delaware data, since there's less of it. So we had the county, which is Kent, Newcastle, Sussex. We had the population, we had our quotas, same as before. Now, we have the same lower quota. I'll just go LQ here. 7, 24, and 9. Right? So the next thing we want is square root of n, this is n, times, oops, times n plus 1. So this would be the square root of 7 times 8, square root of 24 times 25, and the square root of 9 times 10. So now we need to calculate these. Okay, this is 7.4833. This is 24.4949. And this is 9.4868. Real quickly, there's two ways to do this. You should have a square root on your calculator. Mine, I have to push a second button to get it. When you push the button and you bring up the square root, you should get the symbol and this. So what you need to do, like for this first one, is simply put 7 times 8 and then close the square root. And hit enter, and that'll give you the answer. Another way you could do it is figure out what 7 times 8 is, which is 56. And then do the square root of 56, same way. Or you could do 56 and use your caret button to the 0.5. Any of those methods would work. So now let's go back and check what we do next. If the quota is larger, round up. So if this is larger, you go up. So 7.41, 7.48, it's not. That stays the same thing. 24.58, 24.49. This is larger, so we go up. 9.00, 9.48, it's not, so we stay the same. And that gives us 41. And a lot of these, especially with these smaller states or the smaller number of areas, you'll get the same way using all the methods, or the same totals using all the methods. That's not necessarily the case. Usually if there is a difference, it's not significant. So we won't look at Rhode Island again. And we're not going to do the comparison of Webster's and Huntington Hill. This is the last method to look at. This is called Loud's method. So again, the first step, same thing as before. Determine the number of people. Find a divisor. Okay, divide each state's population by the divisor to determine how many representatives it should have. Same thing as before. Cut off the decimal part. Add up the remaining whole numbers. Same as before. This is the only thing that's different. So let's bring all this up again. And then we'll look at 4. So we have our quota. 7.4111. 24.5872. And 9.0017. So our lower quota is 7, 24 and 9, which is only 41. So now let's look at step 4. Assuming that the total from step 3 was less than the total number of representatives, divide the decimal part of each state's quota by the whole number part. So what does that mean? We're going to divide the decimal part by the whole number part. So let's start with Kent. The decimal part being 0.4111, and we're going to divide that by the whole number part of 7. And this will give us 0.0587. And then we're going to divide our 0.5872, divide that by 24 for Newcastle. And that's going to give us 0.0245. Then the last one is the 0.0017 divided by 9, and that gives us 0.0002. Now here's what it says to do. Assign the remaining representatives, one each, to the states whose ratio of decimal part to whole part were largest. So we have our ratios. Let's go ahead and write them on our chart here. 0.0587, 0.0245, 0.0002. Looks like this is the biggest ratio. So they get another one, and the rest do not, because we only need one more. Because this was 40, not 41, and this is 41. And that's the only one that was a little bit different. So that's the 5 methods. Like I said earlier, if you have issues, feel free to email me with questions. I'll be glad to help. If I see that quite a few people are having issues, I'll either make another recording and work more examples. Some of these are easier than others, so I'm expecting that one or two of the methods will be where the problems are, and we'll be able to just go from there. So the last idea, and you've probably heard of this term, gerrymandering is when districts are drawn based on political affiliation of the constituents to the advantage of those drawing the boundaries. So we'll consider 3 districts simplified to the 3 boxes here. On the left, there is a college area that votes Democratic. On the right is a rural area that typically votes Republican. The rest of the people are more evenly split. The middle district has been voting 50% Democrat and 50% Republican. So, part of redistricting, a Democratic-led community would redraw the boundary so that the middle district includes less of the typically Republican voters, thereby making it more likely that their party will win in that district while increasing the Republican majority in the 3rd district. So here's what happens. This district here is mostly the college kids and a 50-50. So the college kids, this is pretty much guaranteed to be Democratic. The vote. Now what's happened here is all this gray area is 50-50. And then you have this little bit of the college area here. So this is going to be Democratic. Most likely. And then what they've done is they've bunched in the majority of this people in this area typically vote Republican, so they can't affect any of the other districts. So yeah, they're going to lose one no matter what they do. So they might as well put all the Republican voters in one area. And there's a big issue with this, more and more. Keep it in mind, if we can go a little bit into American government, since that's what we're dealing with. This has been an issue for generations, basically since the country was built. They redraw districts every 10 years, just like the census. So essentially, it's who's in power in a state, and that party basically gets to draw the districts, and that's where it can be a problem. But that is all that I have from this. As I said earlier, if we need more examples, we can do that in office meetings or on an individual basis. That's all I have. You guys have a good day, and I will see you next time.